Hello again, my dear apprentices. Maurits here. Now we will use implicit differentiation to analyze a graph or a relation. We've tried to make a graph out of a relation. And I will take one of my personal favorites, and that is y to the power of 3 plus y to the power 2 equals to x to the power of 3 plus x to the power of 2. So that is a relation between x and y, right? If it is a function or not, we may not know right now, but we know at least that it's a mathematical relation. And of course we could try to make x our subject or y our subject here. And technically speaking we can, but nah, you really don't want to. The first thing I want you to try to look for is points, values of x and y that satisfies this. So pause the video for a short while, try to figure out values that makes this true. Okay, have you tried? Okay, I will reveal, of course, the quite obvious. Again, stop it if you can't see it. Okay, now it will be, and I will show you. Of course, this is true for all points x equals to y, right? Because of symmetry, any value for x there, y there, if you put the same value for x there, this must be equal. So we know that x equals to y must be on this graph. And we can actually step by step make the graph over here. And by purpose I don't put a scale on it for the moment being, because we don't know other points, but we say we have an x and a y there, and we know that x equals to y, which will look at the same on all scales, will be part of the graph. Next thing we could look for is zeros. Okay. And zeros is of course values where points where the y value is 0. So if you plug in y is 0 to this, so y equals 0, so that will make this 0, right? So we get 0 equals to x to the power of 3 plus x to the power of 2 equals x square x plus 1, right? And that will give us that x is either 0, which is a problematic thing, right? Because we know that x and y is 0 is a part of the graph, and we also know that the derivative definitely is not 0 there. Oh, sorry, wrong. We know that that is a point of the graph already. So, the other thing I said is later on. Secondly, we know that we will find a solution at x equals to -1, right? So now we maybe can put some scale here. I put it over here, say -1, 1, 1, and -1. And we know we have a point there. Then we can look at y-intercepts. Normally for functions I would say y-intercept, but we don't know for the relation if we might have more than one. Okay, so I put x equals to 0 instead, and by symmetry we will get y equals to 0 and y equals to -1. I mean, it's the same problem like this, but now this will be 0 instead. And of course that will give us a point when x is 0, y will be -1, so we have a point down there. Okay, then we should look at critical points. We will start with points where we have an horizontal tangent. In other words, where y prime is 0. And to be able to do this, we need to find the derivative of our function. And now we need to take the derivative of this using implicit differentiation. Stop the video in a few seconds and try to find the derivative of this. The whole thing there. And I will be back in a few. Actually, I will be back all the time because you stop it, but you know what I mean, I guess, I hope. Okay, let's take the derivative of this one. If you haven't tried, stop, try. Okay, now I'll show. That will be 3y squared, right? That is the outer derivative times the inner derivative, which is y prime. Remember this, that y is regarded here as a function of x. We could of course do the opposite, but we choose to because of old habits and because also we want to find this, right? We see that y is a function of x. 3y squared plus times y prime plus 2y prime equals to 3x squared plus 2x, right? And now we put derivative to 0, so that will give us the equation 0 equals to 3x squared plus 2x, or x times 3x plus 2. That will give us a solution x equal to 0. And now it comes to the problem I said before. If y is 0, because we know that at this point if you plug in x is 0, we get y is 0. So if y is 0, or we get to this minus 1 here, we can see that the 0 is a problem, because if we plug in 0 into this, we will be at that point, and there we can see the slope is definitely not 0. But we also, if we plug in, as we said before, 0 into this, we get y is minus 1, right? And according to this, we should have an horizontal tangent there. Now we can plug, of course, in to find the y value. We also find another x value, right? X equals to negative 2/3, right? If we solve this by the null factor law, solve this one. And what we can do is plug in this value into our original relation. So we get that y to the power 3 plus y to the power 2 equals to negative 2/3 to the power of 3 plus 2/3 to the power of 2. That will give us negative 8 over 27 plus 4 over 9, right? That will give us, I turn this to 27th, right? And if we do the math, we get 4 out of 27. So, how to solve this one? First, we can notice by symmetry that if I plug in minus 2/3 for x here, and I plug in the same for y there, that must be a solution. So, in other words, we know that y equals negative 2/3 must be a possible value here. Okay. Since we now know one of the zeros of this cubic equation, we can, with a bit of algebra, figure out the other ones, and we will find that y equals to 1/3 is a solution to this. So if the derivative is 0, we have that y equals to 1/3 at x equals to negative 2/3. Okay, so x equals to negative 2/3, we are somewhere over there. Then y is about 1/3, so we are somewhere up there, and there we have horizontal tangent. For the vertical tangents, vertical points, in other words, where the x, the y is 0. Think about that. Vertical ones means that the slope is like this, right? So if we take the derivative with respect to y instead, we will see this as that the derivative is 0 now. And by symmetry, because the problem is completely symmetric, we will see that we must have a point where y equals to what do you have here? Negative 2/3, and x equals to, oh wait a minute, that is the one we found, right? Let's see, so think right here, we swap these simply. Yes, let's see here, so make it right. 1/3, yeah, if y equals to negative 2/3, x should be equal to, I did do right, x should be equal to 1/3, and we'll have a point over there, right? We can also guess that something particular happens at 0, 0, since we get two different derivatives there, and at when we plugged in here 1/3, okay, we have a few points in. Let's just stop there. So we have these points, that, and we can also, by a little reasoning, figure out that something special happens over there. You can try it yourself. And if we connect this, it looks like this could possibly be an ellipse over there. Is this true? Have we analyzed the graph? What you can do is you go to GeoGebra, for example, and enter these relations. You just go to the input line, write this very expression, enter, and out pops this very thing here. So we have been able to analyze this graph in a rather nice way. I have done this thoroughly on my homepage. I will put a link to that in the description of this, and you can go in and have a look at this. There is several similar relations analyzed, and it's done way deeper than you usually or any time would need to do that for the course, but it can be nice to see and to see how far you get. There's variants of this that you can just find on the same page. Okay, I hope this helped a bit. Thank you.